Hello and welcome to this webinar. I'm Cyprian from Analyses for Safety, and I'm with Piotr Stepien today.
Yes, hello everyone.
So the topic today will be about handling the pressurized system with finite element analysis, and Piotr is our specialist and our speaker.
Okay.
So Piotr is a professional structural analyst with over 10 years of experience in FEA and in different products like Nastran, FEMAP, Midas NFX, ANSYS, and he has more than 30 webinars on different topics. And today he will present you a lot of interesting knowledge about the pressure vessel analysis. And so you know about the blog Analysis for Safety, so this is the first webinar we are doing. And it will be so the purpose of the blog is to raise the awareness of the design challenges in the pressure vessel industry, because there are still a lot of incidents and accidents, and we provide a discussion platform for sharing articles, and I hope you will join the blog and add your discussion to the thread. Well, I'm letting the... Okay, Piotr, you can go on.
Okay, thank you, Cyprian. Hello everyone once again. This is Piotr speaking, and let's start our webinar. So, as Cyprian said, the main topic for today is handling pressurized systems with FEA. So at the beginning, I would like to explain few things, starting from the idea for this particular session. So the main idea is to try to provide you general picture about handling pressure vessels design with finite element method. And basically what we want to give you today is a short guide about few of many important aspects from pressure vessel problematics. So we also believe that the content presented today will be discussed in more detail by you, especially on this portal, and it will give some valuable value for all of you. I mean students, beginners, and professionals. So for the same reason, I would like to say something to professionals. So today maybe it will be a little bit bored for you, but I would like to invite you to stay with the session to hear through a recording later if you don't have the time, and I'm asking for your comments and valuable help and activity, let's say in the future. So I will do all my best to highlight the important key points for pressure vessel analysis, and in the same time, let's say I know it's not possible to talk about everything in detail today, and due to this I would like to apologize all of you, but in time we will try to explore in detail much more topics, and actually as many topics as it possible. Okay, so let's start from these pressurized systems, and from the moment I would like to start from simple definitions which are related to today's topic. So pressurized systems and some related examples. So let's start from the basic example of the steam heating system. And this kind of system is commonly used for home central heating in domestic and small commercial buildings. So if we take a closer look on this system, we see that it consists of a number of sets of pressure equipment, such as piping system, boilers, pumps, radiators. And based on this, we can follow up the definition of pressurized system, which has been taken from the European directive, which defines the pressurized system as an assembly of several pieces of pressure equipment which contains or is liable to contain a fluid like gas or liquid, and is assembled by manufacturer to constitute an integrated and functional whole. And as you see on the slide, the other examples are like pressurized process plants and piping, refrigeration systems, and other which consists just mentioned sets of pressure equipment, as I said. So pressure equipment, as you see, is very simple to define, and it's very simple to make some categories from this. So basically it means vessels, piping, safety accessories, and pressure accessories. So for example, piping hoses, pressure gauges, pressure indicators, of course, some kind of valves, and of course pressure vessels are the components of complex pressurized systems. So if you take a look on just mentioned pressure equipment example specification, it is very clear to realize how big challenge is to design the whole pressurized system. And basically each of the pressure equipment part has got different operational functions, design requirements, different physical phenomena govern their response and behavior, and generally speaking each of them can be subjected to different FEA analysis, verified and modified in regard to numerical simulation result. So, but today we will focus on pressure vessels and related topics, starting from the classification. And there are several pressure vessels definition. On the presented slide, I am citing two of them. So when we are thinking about pressure vessel, we can imagine a closed container which is holding the gas or liquid at the pressure which differs from the atmospheric pressure. So the pressure may come from an external or internal source, or by the application of heat from a direct or indirect source, or any combination of that. So as you heard, some of you probably noted that I have just cited ASME code. But additionally, I would like to introduce the term vessel, the vessel itself, to provide you right direction for the understanding the rest part of the presentation. So the term vessel, the vessel only means housing designed and built to contain fluids under pressure, including its direct attachments up to the coupling point connecting it to the other equipment. So generally vessel may be composed of more than one chamber, and I'm citing this ASME again because actually it's very important to know that today we will not talk about the pressure containers, which are some integral parts or components of mechanical devices like pumps, compressors, turbines, hydraulic or pneumatic cylinders. And basically the reason is the reason sounds like that. For them, the obtained stress comes from the functional requirements. This is the main reason, and we are talking about the pressure vessels which are used in a variety of applications in industry and private sector, let's say. So they appear in these sectors as storage vessels, autoclaves, and they are widely used, for example, in mining operations, oil refineries, petrochemical plants, nuclear reactor vessels, and the others. And due to that, they can be categorized based on following criteria, like, for example, shape, wall thickness, manufacturing methods, loading application installation methods, and others. And generally on these slides 10 criteria has been presented, so I will not say anything new right now, but having this classification awareness is crucial for making good design and making good analysis decisions. It's good to have this awareness in case of proper resources selection, especially for finite element approach. So considering the shape, theoretically pressure vessels can be almost any shape, but shapes made of selections of spheres, cylinders, and cones are usually employed. And a common design is a cylinder with end caps called heads. So head shapes are most often round, circular, or shaped like a dish. More complicated shapes have been more difficult to analyze for safe operation, and they are usually far more difficult to construct. But depending on the type and purpose of the pressure vessels, they have some number of the openings, especially if we take a look on this pressure vessel to the left. So openings in the pressure vessels are necessary to carry on normal operations, and they allow for mounting of equipment, the insertion of instrumentation, and the connection of piping to facilitate the introduction and extraction of content. And openings are generally made in both vessel shells as well as heads, as you see on the picture. Unfortunately, these openings also result in penetrations of the pressure restraining boundary, and such are seen as discontinuities. And this is the term that will appear many times in your practical design procedures. So discontinuities weaken the pressure vessel strength because they are simply sources of stress concentrations. And this is very important to know. So let's take a look on the next slide. And from this point of view, from this slide, we have to think about the pressure vessel from the, let's say, safety point of view. Pressure vessels, similar to other mechanical or structural components, are not indestructible, and they can fail catastrophically, kill and injure workers and the others, and cause extensive damage. So reported data shows us that most pressure vessels accidents come from operator error or, let's say, poor maintenance, but accidents which are caused by wrong design and fabrication are still present even these days, and they cannot be trivialized, especially in regard to unmeasurable consequences of failures like, for example, serious injuries or loss in human life. So based on presented data, almost 14% of total incidents had been caused by wrong design or fabrication. So at the bottom of this picture you can find a link to some organizations which provides this report, and we strongly, let's say, recommending this procedure to investigate this data. The many reports consist of excellent remarks, and they are providing excellent knowledge what actually happened to the pressure vessel. Okay, so as the example, I will mention Marcus Oil accident, which happened in Texas in USA in 2004. So it's not so much time ago. And this facility refines polyethylene waxes for industrial use. So the waxes are processed and purified inside a variety of steel process vessels, and they contain flammable hydrocarbons such as hexane. And the vessel that exploded was very huge. As you see, the dimensions were 12 feet in diameter, 50 feet long, and the weight of the pressure vessel was about 50,000 pounds, which is almost 23,000 kilograms. So explosion throwing heavy fragments into the community, which damaged neighboring buildings like church, for example. It damaged car windows, and this happened due to improper modification and faulty welds of the vessel. So as I said on the previous slide, we saw some reasons like wrong design or fabrication. Now we have the third reason for the accident, which is improper modification. So pieces of shrapnel metal weighing over 450 kilograms traveled at extremely high speeds, up to a half mile before landing or on nearby highways and railways. So this depicts very well the scale of the explosion. And what is important, 3 plant workers killed and several residents were cut by flying glass. And just let's take a look on the next example. So this example refers to the NDK Crystal Company, which is a manufacturer of quartz crystals in USA. And in this case, there was an explosion. There was sudden explosion of the pressure vessel, and this case also provides excellent information about the scale of the explosion. So the fragment skipped across, for example, one of the fragments from the pressure vessel skipped across neighboring facility parking lot and slammed into the wall of adjacent business office. And those, let's say, accidents demonstrates the potential danger of pressure vessels, and once again I will say scale of consequences if they are not properly designed, constructed, operated, inspected, tested, and or repaired. So the higher the operating pressure, then the larger the vessel, the more energy will be released in a rupture, and the worse will be the consequences. And it's supposed to be, or let's say, it should be emphasized that the danger exists even if the vessel contents are not flammable, reactive, or explosive. So to avoid this catastrophic scenario, the design of pressure vessels is often strictly regulated by codes in order to ensure that the products are safe and functional. So today, two commonly used codes for pressure vessels operating in the process industry are American ASME code and European, let's say, counterpart. So the ASME 6 division, ASME 8 division 2, for example, refers to the methods related for the designing, and European code with the number EN 13445 for example. So but both of them provide rules and, let's say, minimum requirements for the design, materials, fabrication, and inspection of boilers and pressure vessels. And other no codes are British Standard, which is currently available as published document PD 550, and is published by British Standard Institution. But these days, let's say, it has been replaced, and all of the codes are harmonized with the Pressure Equipment Directive if we are talking about the European Union. So both mentioned codes, I mean ASME code and European code, EN code, provide two design sections which are offering two approaches for the design. And their names are designed by rule, or let's say designed by formulae, and the second one is designed by analysis. And starting from design by rule, this section contains a set of rules based on strength of the material equations and empirical formulae, and the designer simply follows the rules laid out in the procedures for the basic components like nozzles, heads, cylinders, flanges, and so on. So, for example, there are cases when the loadings and geometries are such that the procedure cannot be applied effectively, and this happens when designs are very complex. It's not possible to for example, it's not possible to provide equations for these areas. For example, if there are a lot of nozzles or other discontinuities, and it becomes difficult to apply this approach without big margin of safety. So this solution is not economical sometimes for the basic, for the complex solutions. And to cover the design of more complex shapes, second approach, which is called design by analysis, was written to use results from numerical analysis, and based on that make the design more accurate and open for more complex configurations. So design by analysis mainly prescribes criteria for any kind of loads and geometries which are not explicitly covered by DBR. So this design approach provides a much more rational safety margin based on the actual stress profile, and optimizes design to conserve material, leading to consistent reliability and safety. And of course, I don't want to talk about the differences between the codes at this moment, but as we see from the picture, the both codes have similar structure. And as I said, design by analysis approach stands for this, which is our objective when we want to perform analysis using finite element. method. So let's continue the speech about this. Design by analysis criteria are written in terms of design checks. So these design checks are given to protect against 4 different main failure modes. And methods are described for evaluating against gross plastic deformation, which is the basic static failure mechanism considered by DBA, incremental plastic collapse, buckling, and cyclic load. So for DBA, as you see, 2 roads exist. The linear stress classification route and the direct route, which refers to inelastic or let's say plastic analysis. And for the elastic analysis, for the elastic stress analysis method, a linear elastic model is used, and this means that the stress in the material is assumed to be linearly proportional to the strain, also above or let's say beyond the yield stress. So this method is also called stress classification method, and nonlinear methods assume nonlinear behavior of the material beyond the validity of the Hooke's law. But for the moment I will skip this topic and we will back to this topic later. So now we will start from the gross plastic deformation, and we will follow up the procedure, let's say, in referring to the code. So at this moment I would like to introduce what the gross plastic deformation is. And as I said, this is the basic static failure which is considered in DBA, and the wall thickness of the vessel must be great enough to ensure that this failure does not occur. So unless the load is limited, this ultimately leads to plastic collapse or rupture of the vessel. So the form of plastic collapse mechanism differs between structural configurations, and this is why those pictures has been presented, because in some cases the entire volume of the structure experiences plastic deformation and failure, but in other cases only local regions of the body experience plastic straining, with the rest the rest remain elastic. So as you see, the picture to the left describes the first situation, so we can observe when the wall experiences plasticity, let's say full or global plasticity. And to the picture to the right, we are observing the simply supported beam, and now using the contour of the plastic status, we are observing the local plasticity. Okay, so now let's start to talk about the stress categories. So there are 2 approaches to avoid, let's say, gross plastic deformation, and both of them are specified in the code. So I'm talking about the linear approach and nonlinear approach. And when the linear elastic analysis is used, the allowable load is calculated indirectly by partitioning the elastic stress into primary, secondary, and peak categories, and limiting the primary stress to a specified allowable value. This is very important, the last part of the sentence, what I said, limiting the primary stress to a specified allowable value. And generally speaking, design by analysis approach works in this way. So different stresses have different degrees of importance, and this is why they had been categorized in the code. Once again, we are talking about the elastic approach, and now we are what we want to do is to perform categorization of the stress. So before that, it has to be understood what are the loads which will act on the geometry. So there are several different load cases that need to be analyzed, taking into account different scenarios during the lifetime of the vessel. So usually 2 cases are analyzed. Let's say design loads and operating loads, and based on the loads, elementary stresses are calculated at all points basically, yes, exactly like that. Elementary stresses are calculated at all points that are in scope of the analysis. Okay, this is what I wanted to say. In a three-dimensional case, once again, in the three-dimensional case, these elementary stresses consist of a vector of 6 components of normal and shear stresses, which finally should be classified as membrane or bending stresses. And the code categorizes the stresses into 3 categories, and the main task for the designer of FEA engineering is to classify resultant stresses to the right category. And from this moment, let's talk a little bit about those stresses. So basically, primary stresses are the most critical stresses for the design, meaning that if they exceed yield stress, they will lead to failure without any doubts. They are caused by mechanical loads, and they are needed for fulfilling the laws of equilibrium, of moment, of forces and pressures. And primary general stresses are characterized by not being self-limiting, which means that they are distributed within the structure so that no stress redistribution will occur as the result of yielding. An example of primary stress is the hoop stress within a pressure vessel induced by an inner pressure. By increasing the pressure, the stresses will increase until yielding. And there are 3 subcategories of primary stresses: general primary membrane stress, primary bending stresses, primary local membrane stresses. So general primary membrane stresses, they are self-explanatory. So membrane stresses with the characteristics of primary general stresses. So it's very easy. And these are found remote from large discontinuities. So these are found far from large discontinuities like cone-cylinder intersections and nozzles. And examples of general primary membrane stresses are membrane stresses at the center of a flathead, or circumferential and longitudinal stresses with a pressure vessel. Bending stresses are those ones that fulfill requirements of primary general stresses. One example is bending stresses at the center of a flathead of a cylindrical pressure vessel. Local membrane stresses are type of membrane stresses and that are present near structural discontinuities. You can find them close to structural discontinuities. And they have some characteristics of secondary stresses. And finally, secondary stresses originates through the self-constraint of the structure, and this type of stress must satisfy the imposed strain or displacement as opposed to being in equilibrium with the external load. So this type of stresses are called being self-limiting. They are self-limiting, or sometimes you can meet them definition like they are self-equilibrating, and which allow them to exceed yield, since small plastic deformations will redistribute the stresses to other parts of the structure. And finally, peak stresses are the highest stresses in the regions produced by concentrations, and they are mostly responsible for the fatigue failure. So, as I said before, the computed stresses should be compared to material-specific stress limits, and depending on the code, the stress limits are marked as S, like in ASME code, or F in European code. And for each stress category, stress intensity is defined. So if we take a look on this slide, we can see that let's say for the first 2 stress intensity limits, we have assurance that the vessel will not fail against gross plastic deformation. The third, let's say, stress intensity limit ensures that vessel will not fail by ratcheting, for example. So, but let's say for FEA, the situation is not so easy in terms to classification for the stress limits, and depending on the element type, any kind of finite element software provides different result data. And for two-dimensional element, which is recognized as shell or plate depending on the code, results such as membrane and bending stresses are obtained directly and they are compatible with the code requirements. But in case of three-dimensional analysis, as I started to say before, the stress at the point is defined by 6 components. Usually those components are oriented with respect to the global coordinate system, and these results are not in agreement with the code requirements. And due to this fact, a technique which is called stress linearization has been developed, and the method is widely used for separation, or we can say extraction, of pseudomembrane bending and peak stresses from solid element linear result. And the stress linearization procedure is valid on, let's say, for the ratios like diameter to thickness ratios with the value of 8 or greater, and below that the calculated shells are no longer thin and the stress distribution through the thickness is not linear. So there are other, let's say, mechanics is governing this type of phenomena, and they become significantly nonlinear. Below that limit, which means below the 8, limit law or elastic plastic analysis is appropriate, and I will talk in few minutes about that. So the second important thing related to the stress linearization is to check how your software is performing this linearization. And the process must be with the agreement with annex of the ASME code. So actually I didn't provide the number of the slide, but this is 5th annex 4.1.2.b.1. So let's say we can put this information on our blog. And this is very important to check how your software is doing this process, because most of the commercial softwares are don't following these rules, and this is one of the requirements of ASME codes. So in other cases for, let's say, stress classification, actually there are many challenges in regard to this process. So all the time we have to ask ourselves where to put the valid stress classification lines. The next question is how to properly classify the stresses, how to properly classify primary, secondary membrane bending. And what if the linearized stress result is ambiguous? So this type of questions are very important, and usually the FEA pressure designers are facing all the time. And there have been a number of discussion of this topic. You can find a lot of information on the forums. But the object of the whole exercise, I mean the object of the stress linearization, is not to find a linear profile of the stress, but actually is to sort them statistically determinate stress components from the indeterminate components and peak stresses. So the topic of stress linearization has been presented in the document, which has been shown on the slide. It has been released by the Welding Research Council, and the name of the document is WRC 429. And basically this is the report about linearizing at the component level, and then about calculating the stress intensity. It's a little bit old, but it sets for the physical basics for linearization, and it's very good for starts. And a lot of guides from this paper has been implemented inside the ASME code in regard to this process, in regard to the stress linearization. So you can find inside a lot of important topics like how to relate the failure mechanism to the failure, how to perform this this separation process, how to classify this stresses into primary and secondary. Actually, it's not about how to classify, but it will provide you the guides how to start how to start. And of course, it's about the stress linearization. And now we are starting to talk about the nonlinear methods. So basically, we can perform the calculations. We can design our pressure vessels against the gross plastic deformation using elastic method and nonlinear methods. And there are two types of inelastic analysis which are maybe used. So first one is limit analysis, and the second one is the plastic analysis. So limit analysis assumes an ideal elastic, perfectly plastic material model and small deformation theory. So when perfect plasticity and small deformation theory are assumed, the load carrying capacity of the structure is limited by equilibrium considerations, and a plot of applied load against resulting deformation for limit analysis is shown to the left. So initially the structural response is linear elastic, but as yield is exceeded, regions of plastic strain develop and the response becomes nonlinear. So as the loading continues, equal increments of load cause increasingly greater plastic deformation, and the plastic zone expands to equilibrate the internal and external stresses with the externally applied forces until a stage is reached when no further expansion of plastic zones can occur to accommodate the applied load increase, and this is called the limit load. So basically we are talking about the region for unlimited flow, which describes the plastic collapse. However, real structures may behave differently to the limit analysis model in two ways. So the material may exhibit post-yield strain hardening and also can exhibit large deformation. So as strain hardening materials can support stresses greater than yield, plastic deformation can continue for loads above the theoretical limit load of the structure without violating the equilibrium. And changes in structural configuration as loading progresses can also affect the load carrying capacity of the vessel. If large structural deformations occur, the structural load spread may change, and this can increase or decrease the load carrying capacity of the vessel. And in design by analysis terminology, the elastic plastic analysis, including strain hardening and large deformation effects, is called plastic analysis. And this has been presented to the right picture on the past slide, actually. So at this moment, we see some example of limit stress analysis. The analysis has been performed inside FEA software. So what is important that there is no good guidance in the code, and the code doesn't say anything about convergence criteria. The code is not giving you the clues how to perform the analysis itself. So it's very important to start learn FEA from simple basics, from the static analysis, and after that you can start to learn about nonlinear methods. Small displacement theory, how to apply that. Usually in the software there is an option which is called geometry nonlinear or large displacement option, or LG-DISP parameter, depending on the code. For the Nastran is, for example, large DISP. And you have to be aware that for the perfect plastic material and small displacement theory, this checkbox supposed to be free. It's not allowed to check that. And the other methods are like elastoplastic methods, and these methods are applicable also for the gross plastic deformation, but usually what is important, they can be used also to analyze, or let's say to study, the incremental collapse, which is related to the low cycle fatigue problems. And the incremental collapse has been divided into the shakedown and ratcheting. So if we take a look on this curve, and if we consider a load, let's say, which is sufficient to cause the vessel to yield at 0.8, and then we can perform some straining, harden to B. So when the load is removed at the residual strain, we achieve the point C. And when a load of the same magnitude, let's say, is reapplied, the strain is reapplied, let's say, the strain returns to B, and on unloading returns to C. So after the first application of pressure, the magnitude of the total strain remains constant, and this cycle of events is known as shakedown. But next, if we consider a much larger load which causes the vessel to strain harden to D, and when the load is removed, the strain returns to E. So when the load of the same magnitude is reapplied, the strain goes to F and then returns to the G point. And on each cycle, there is an accumulation of the strain, as you see. And this accumulation of strain is known as the ratcheting and will lead to failure by incremental plastic collapse, for example. And on the next slide, we are seeing the results from for the head of the toruspherical pressure vessel. So axisymmetrical model has been used, and large displacement theory as well. So for this type of analysis, you can simply use nonlinear analysis with Newton-Raphson algorithm for the solution, but it can provide you a lot of problems with the convergence, and this is why Arklert method is also widely used for studying of these problems. But what is important, we will not talk in detail about these types of analysis today. Actually, as I said at the beginning, the main reason of this webinar is to provide you some scope of the problems, and we believe that in time we will provide you much more detailed webinars, much more detailed videos and articles about particular problems, starting from these problems which has been presented on the webinar. So right now, actually, that's all from my side, so I'm leaving the voice to Cyprian, and he will conduct the rest part of them.
Hello everyone, so I'm back. So I'll have just a few words about FEA analysis in pressure vessel, because if you ever used FEA analysis, you know that it's not always useful to actually perform FEA analysis, and in some cases it's just actually a loss of time. So it's important to be able to determine this when you are working in pressure vessel design. And in cases in which a code equation are not giving any doubts, then you don't need to use finite element analysis, because it will be a waste of efforts. But if in the pressure vessel design the decision is frequently left to the designers, and FEA analysis is useful to clear out the doubts about the safety at some particular complex nozzle or discontinuity. Finite element analysis is almost always required when there are several nozzles and the shape is complex, and also when the temperature conditions are taken in account. So accuracy in finite element analysis depends also a lot on the mesh, and you need to have the right tool in your software to construct a really good quality mesh. So for example, map meshing is a must, and then you will need manual meshing operations like the extrusion of some shape, and you will be able to get the correct stress at some specific point of your model. So if you're interested by knowing more what are actually the requirements for the accuracy of the solution, then I advise you to check this AB 520 standard set out by the APSA, so Alberta Boiler Safety Authority. So you have the link here. It's a very interesting document, and you will find what are the advices to follow in order to get accurate analysis. So it's all for today's presentation, and now we'll have very short question session. So if you have some question, please ask them in the chat, and then Piotr Stepien will answer them.